God's understanding is infinite. Numbers are an aspect of God's mind. Who would have thought that when you run numbers through that little formula, you get that shape? It's remarkable. Nobody was expecting that.
Today I want to cite a deduction from the various teachings, rational teachings about God and the universe. You cannot find God at the end of anything physically or materially. He is not there. First point. It's just simply a case of the more you look, the more you see, and the more you seek, the more you would find. Okay guys, so let's take a simple look at this mathematical equation of the Mandelbrot set, which gives us an insight as to what we're talking about. Take a look at this mathematical equation. Stay tuned till the end.
So we're going to talk about a particular set that's called the Mandelbrot set. This was discovered in the late 1970s, early 1980s, named after the person who really discovered this, Benoit Mandelbrot. He was a math guy and a computer guy. He worked at IBM. This set is defined according to this little formula that you see right here, where it's the set of all numbers, C. C is a number that is potentially part of the Mandelbrot set. We're testing it, for which this other number, Z, remains small according to this little formula. And it looks very complicated, but it's really not. I'll take you through it. The little n just means that that's a particular value of Z. N plus 1 is the next value of Z. So there's lots of values of Z. There's a sequence. And if that sequence of Z stays small, then the other number, C, is part of the Mandelbrot set. On the other hand, if the sequence of Z gets very big, if it goes 1 to 100, a million, a billion, then C is not part of the Mandelbrot set. And we'll do a couple of examples to let this sink in. It's pretty straightforward, really. So we're going to ask, is the number 1 part of the Mandelbrot set? So C equals 1, okay? And we're going to plug that into our formula then. So we have Z squared plus 1, because that's the number we're testing. That becomes the new value of Z. Now the first value of Z is 0 by definition. So that's the first value. So we plug that in, and we have 0 squared, which is 0, plus 1 is 1. Yeah, 0 squared plus 1 is 1. So that's the next value of Z, okay? And what we'll do is we'll put that 1 back into the formula. That's the new value of Z. So now we have 1 squared, which is 1, plus 1 is 2, okay? And you plug that back in, so we have 2 squared is 4. 2 times 2 is 4, plus 1 is 5. Okay, you're getting this. You put it back in, 5 squared, 25, plus 1 is 26. Okay, we put that back in. 26 squared is a big number. And you put that back in. Okay, now you see what's happening here? Is the sequence of Z staying small? No. So is the number 1 part of the Mandelbrot set? No, because it has to stay small for it to belong. There's one more complication, and then we get to the really cool stuff. The other complication is that the Mandelbrot set also includes what are called complex and imaginary numbers. Okay, so an imaginary number is a number that when you square it, you get a negative number. And that's a little hard for us to understand, and so they call them imaginary. It's just a name. I hate that they have that name because it makes it sound like they don't exist. You know, they're fabricated. No, they do exist. Imaginary numbers do exist. And to add insult to injury, the numbers that are not imaginary they call real. But that's just terminology. Both are equally true, let's put it that way. But how do we have a number that times itself is negative? And it's represented by a lowercase I. That's the kind of the primary imaginary number when I times I is -1. How do we make sense of that? After all, imaginary numbers are not positive because a positive number squared is positive. And yet, the imaginary number times itself is negative. Imaginary numbers are not negative because a negative number squared is also positive. And imaginary numbers are not 0 because 0 squared is 0. Weird. So we have a number that's not positive, it's not negative, and it's not 0. And that leaves us kind of scratching our heads a little bit. We have trouble with that. Well, I got news for you. Not everything in this universe is intuitive. If you've ever had a class in quantum mechanics, you know, the universe doesn't work always the way that we expect it to. You know, our intuition really is based on experience. And the fact is most adults don't have experience with imaginary numbers, and so they seem strange. But it's just a matter of experience. When you were a little kid, negative numbers probably didn't make a lot of sense, right? You know, I can have 1 apple, I can have 2 apples. How can I have -2 apples? That doesn't make sense. How can you have less than nothing? You get a little bit older, you get a bank account, suddenly negative numbers make a lot of sense, right? Yes, I can have less than nothing. Well, imaginary numbers are the same way. You gain a little experience and you find, yes, there are numbers that when you square them, you get a negative, but they're not positive, they're not negative, and they're not zero. How do we make sense of that? One way to do it is if you consider a number line. So here we have a number line. Now, the positive numbers are to the right of zero along that number line. The negative numbers are to the left of zero along that number line. So how do we represent a number that's not positive, not negative, and not zero? Well, you put it up above the number line like that. It's not on the number line, it's on a different axis. And by multiplying I by the other real numbers, you can have all kinds of imaginary numbers. And you can think of them as being on a different axis. So the real numbers are along this axis, the imaginary numbers are along that axis. And that makes sense. You can see that the imaginary number, it's not positive because it's not to the right of zero, it's not negative because it's not to the left of zero, and yet it's not zero. That kind of makes sense. And then you can also have numbers that are called complex, and they're off axis. They're called complex because they have a real part and an imaginary part, but it's one number with two parts. And usually the real part is represented by the x-axis, and then the imaginary part is represented by the y-axis. And so you can plot any number in a plane by those two components, the real component being the x and the imaginary component being the y. That's kind of neat. I can represent any number on a plane. Very convenient. So the Mandelbrot set also includes these imaginary and complex numbers. And the only thing you need to remember, they obey all the ordinary rules of algebra. It's just that when you multiply I by itself, you get -1. That's the only thing you have to remember. What we can do then is we can make a map, because I'm trying to figure out if there's a pattern to the numbers that belong to the Mandelbrot set. And it turns out there is. But it's not obvious, right? Because you can't tell just by looking at a number whether it's going to belong or not. You have to run it through that formula, and that's kind of tedious. But in the 1980s, computers were starting to get fast enough where they could iterate that formula a number of times, and they could analyze to see whether z is getting big or staying small. And so what we can do is we can have the computer check all these different points, and we'll see if there's a pattern to the Mandelbrot set. And so we'll take the points that belong to the Mandelbrot set, and we'll color those black. That's arbitrary. That's the way Benoit Mandelbrot did it, and we follow his example. So, and you have the computer check more points, and you find that all those points right there belong to the Mandelbrot set. When you run it through that formula, z stays small. And then the points that do not belong, we'll color those red, or some other color. It doesn't really matter. And so we already checked the point 1. We found that the number 1 does not belong to the Mandelbrot set, so it gets colored red. And had we checked these other points, we would find that they do not belong. And so you see, as you plot more and more of these points, a pattern starts to emerge. What's it going to look like? Well, you have the computer run through thousands and thousands of points. You have the computer check each one of those numbers, and a pattern emerges, and the pattern looks like this. It's really interesting and unexpected. Nobody was expecting that when you made a map of the Mandelbrot set, it would look like that. Remarkable. I'm going to remove the axes now, because it turns out this shape is remarkably interesting and unexpected, and it'll turn out to have a lot of beauty in it as well. The shape itself is, I mean, this is a mathematical plot. I guess we'd expect it would have some mathematical properties to it, but everyone was surprised by the properties it has. The main shape that looks kind of like a heart, that's called a cardioid. And a cardioid is what happens when you take a circle and you take your pencil on it and roll it around another circle of equal size. The shape you'll get is a cardioid. And you can see that, sure enough, the main part of the Mandelbrot set is a perfect cardioid. All the other shapes that are growing off of it are circles. All these perfect circles attached to the perimeter of the Mandelbrot set. And then you see some other features, like these little tendrils that grow off of it, and a spike over on the left, kind of that juts out. That's kind of interesting. You notice that that top circle there, it's got a circle on top of it, another one on top of it on smaller and smaller scales, and it goes out and forms this little tree, and it's got 3 stems to it, including the trunk. So it's got a trunk and 2 stems for a total of 3 branches. You see that there? Now the next one to the left branches into 5. Can you see that? I mean, it's kind of small, but you can see the 5 branches there. The next one is 7, 9, 11, 13, 15. It's all the odd numbers. And by the way, they don't stop. They go to infinity. There's an infinite number of them. They get smaller and smaller, though, and so you have to zoom in more. So somehow the Mandelbrot set knows how to count. It's kind of remarkable. And then on the other side, you have the odds and the evens. You have all the numbers there in terms of the number of branches. Now, it's remarkable enough that they have branches at all, because who would have thought that when you run numbers through that little formula, you get that shape? It's remarkable. Nobody was expecting that. And it's even more remarkable that it has the ability, apparently, to count in terms of the number of tendrils that grow off of each bud there. And of course, you can take two of those numbers, like 5 and 3. Now, 5 plus 3 is 8, okay? And it turns out that the bud in between those two has 8 tendrils. Interesting. And that's true of all of them, both on the left side and the right. The bud in between the two adds the number of tendrils on each one. So not only does the Mandelbrot set know how to count, it knows how to add. And then on the left side over there, you got this kind of spike that goes out. And you see there's this little bump on the end of the spike. So let's take a look and see what that looks like. So we'll zoom in on it. And that little bump, turns out, it looks like the entire Mandelbrot set. It's a mini Mandelbrot set. And it's almost identical to the parent, except it's got extra spikes growing off of it. But the basic shape's the same. It's got the cardioid and the circles. And, it has a little spike growing off of it, too, with a little bump. What could that be? Well, let's zoom in on that. And, interesting. Absolutely fat. And it's got extra spikes growing off of it. And that's got a little bud. How about that? Now, of course, you could do that literally forever. And there's an infinite number of baby versions built into the Mandelbrot set on smaller and smaller scales. And take a look at how small this is compared to the original when we zoom back out here. Look at how tiny it is. Isn't that remarkable? And the fact that it repeats infinitely, and it doesn't lose complexity, it actually gains it each time you get more extra spikes growing off of it. Very remarkable. Well, to anticipate my conclusion in this, I'm going to suggest to you that this shape tells us something about the way God thinks. God's understanding is infinite. Numbers are an aspect of God's mind. God is responsible for numbers. And so it makes sense in the Christian worldview that when we explore and study numbers, we find intelligence in them. We find evidence of patterns. And not only intelligence, but infinite intelligence, because this thing repeats infinitely. A structure that repeats itself on smaller and smaller scales is called a fractal. So the Mandelbrot set is one example of a fractal. There are other types of fractals. There are other sections of the Mandelbrot set that are fractal. We could zoom in, for example, on one of these little tendril features here and zoom in on that. And you'd say, well, that's interesting. You think what's going to stop at some point, right? Eventually it'll even out and you'll get, but it just keeps going. It's infinitely wiggly, you see. It's wiggling around like that, and you zoom in on it, and it keeps going and keeps going and keeps going. It's just mesmerizing to watch this thing and see the scale here. And it gives you a little taste of what God's mind is like, to be able to think infinitely. We can only process just a little bit of information at a time, but God's mind is truly infinite.
Ideal and simple but seemingly complex mathematical equation that physically shows this, that the more you look, the more you see. And the more you see, the more you realize. You keep going physically, you cannot see the end.